Hi, everyone. My name is Clay Stevens, and I'm a PhD student at the University of Nebraska-Lincoln, advised by Dr. Hami Bagheri. I'd like to present to you today our approach to reduce the runtime adaptation space of self-adaptive systems by analyzing the possible bounds on the utility generated from each system configuration. To start, our motivated domain here is the self-adaptive systems. These are systems that can automatically change their configuration at runtime in response to changes in the environment in which they operate. These systems can be very valuable in certain situations, but it comes at the cost of an exponential growth in the number of attributes that they might need to evaluate at runtime when they're making their adaptation decisions. This can be especially costly for low power or otherwise computationally limited systems like unmanned autonomous vehicles or other sorts of embedded applications. One classic example of a self-adaptive system, however, is that might run a website, some web infrastructure, something like that would spin up a new cloud server in response to increased demand for a website. In this case, there may be two things that the system can change. First, the number of servers that can increase or decrease in response to demand in order to meet certain response time requirements. However, adding more servers would come with an increased cost. Another option would be to change the amount of content that is delivered with each request. In this case, decreasing the amount of content would increase the performance of the website in terms of response time and latency, but it would decrease the quality of the experience for the user. Most of these adaptations, like increasing the content or decreasing the number of servers, might be instantaneous. But in this case, adding a new server would have a little bit of a latency, in that it may take some time for the new server to come online, and the benefits of adding a new server may not accrue instantaneously. In sort of naive brute force approach, the system would react to changes in the environment by evaluating all of the possible configurations at runtime and selecting the one that provides the best utility. That may not take into account things that have a latency, like adding a new server, which is addressed by the state of the arts in this area, which takes a proactive approach in that it looks ahead to see what the value of the configuration may be in the future, and makes this decision based on which adaptations would be reachable in the given time span and would have an impact on the system. Now that can provide better utility to the users of the system, but it still comes to the cost of having to evaluate a great number of states at runtime. Because in this case, we're not only looking at the configuration that we're evaluating to adapt to, but we're also looking at each of the configurations that are reachable to that out to some time horizon. So there's an explosion of states that might have to be visited even recursively with the state-of-the-art approach, many of which will never be chosen. And our insight was that some of these states may never be chosen under any circumstances, that even the best possible performance of a given configuration may be worse than the alternatives that are reachable at the same time. So we sought that we could eliminate these suboptimal adaptations offline before performing the runtime evaluation. And we can do that by comparing the best case performance available at a particular configuration with the worst case performance, and trimming those where the best case is never better than the alternatives. So our approach to this, which we call thallium, starts with two models of the system. First, a structural model, which represents the system as a set of tactics that can be enacted and shows the results of applying each tactic to each configuration. And a behavioral model, where we represent the system as a game between two players, the system and the stochastic environment in which the system operates. We then perform model checking on each one. First, the structural model is checked and executed with the bounded model checker to produce a graph of all of the configurations that are reachable from each given configuration, so that we can see the results of each tactic on the structure of the system. The behavioral model, which again is represented as a game, is run through a probabilistic model checker to determine the expected utility can be generated for each configuration, as well as the best case where the players collaborate and the worst case where the players compete. Those three values are then combined using possibility theory to produce a fuzzy value, which gives us a single metric, which we call the potential for each configuration for each optimization objective. Those potential values are combined with the reachability graph And we perform a Pareto analysis to find the states, or find the adaptations that are dominated by other adaptations available from the same configuration. Those dominated adaptations are removed from consideration, and the resulting trimmed adaptation space is that is used at runtime, greatly reducing computational overhead for each runtime comparison. To evaluate thallium, we asked two research questions. First, we looked at how well thallium does in reducing the size of the adaptation space, which will have a direct impact on the runtime computation complexity of doing the adaptations. And the second is we wanted to make sure that thallium provided comparable utility against the state-of-the-art approaches, because we don't want trimming the adaptation space to result in removing configurations that would otherwise be desirable. We first evaluated the offline space reduction by computing the size of the adaptation space statically. We did this for two exemplar systems. First, SWIM, a simulator of web infrastructure, and DART, a simulated team of drones flying in a hostile environment. And we show that regardless of the weightings that are put on the best, worst, or expected value when we compute the potential, it doesn't really matter what the weights are. We still show a pretty consistent reduction in the size of the adaptation space, between 22% for DART to up to 63% on average for SWIM. Secondly, we ran another experiment specifically on SWIM at runtime to see what the reduction on the number of comparisons is and the utility of the system in general. First, we instrumented SWIM to allow us to count the number of comparisons that are done between given configurations, and we show that we reduced that by about half. We cut the number in half compared to the proactive latency-aware approach. We also show that our utility is just slightly higher, but is definitely comparable. Similarly for DART, the simulated team of drones, we cut the number of comparisons by about 1/3 from around decreasing the number of comparisons that the system would have to do. Again, we showed a slightly higher cumulative utility, and it's definitely comparable, so we're not losing any utility by reducing the size of the adaptation space. In summary, we have determined that thallium is a novel reduction in the runtime decision space. We achieve this by combining two different kinds of formal methods, both a structural and a behavioral system to extract more domain information by comparing the bounds, which was a 30 to 50% reduction in work with comparable utility. We would also like to evaluate some other heuristics and some other comparisons. And we would like to thank both the National Science Foundation for financial support, as well as thanking all of you for coming to listen to my presentation.